So far we have talked about elastic shortening. Now we are getting into the friction losses. Now what is a friction loss? When the jacking force is applied, there is going to be a friction between the tendon and the duct, right? Because this is, we are talking about a post-tension system, okay? In pre-tension system, the steel is directly bonded to the concrete, right? In post-tension system, you put a duct and then the tendons are inserted and then you stress them, and then in a bonded system you grout it. In an unbonded system you don't grout it, typically it will have a grease. But here when you do the stressing process, whether it is grouted or ungrouted, that will happen at a later point. When you do the stressing, the tendon is going to go and rub against the surface of the duct, right. So that will prevent the interior parts of the beam or slab from generating the full pre-stressing force, right. So that is what it is shown here, and typically if you look at it, this is a beam and this is your duct, okay, and this usually wherever we are doing the jacking, that we call that as a live anchor, and wherever you do not do the jacking and you put your anchors, that we call that as a dead end anchor. When you stress them, what will happen is, this is a cable, okay, this is the tendon or a cable. The tendon will move up and try to rub against the surface of the duct, okay. In this process I am going to create some friction forces that will prevent the full pre-stressing force is getting transferred to the concrete. So we have to account for that. Now this friction force will be of course proportional to the coefficient of friction between the duct material and steel, and also the resultant of the vertical reaction from the concrete on the tendon generated due to the curvature. Now the curvature of the cable profile also will come into picture, that we will see from simple schematic. Now in friction losses there are two components, but the essence is this: because of this friction, the force that is available along the length of the tendon will keep changing, okay, that we have to account for that. There will be loss that is happening because of the friction that is being developed, that we need to account for that, right. And this friction losses we need to account for two effects. One is the curvature effect, because the cable itself is curving, right. So the cable is having some profile, so it is having some curvature. Because of that curvature, you are going to have some friction losses. In addition to that, the cable is not going to be straight, okay. So the cable you are assuming like this, but actually the cable may be like this, okay. You will have local waviness will be there in the cable, that we call that as a wobble effect. These two things will create loss in the pre-stress, that we need to account for that. Now let us see how do we do that, okay. Now I am going to take a small free body diagram of a cable of a small length, okay. I am looking at only the free body diagram of the cable, okay. Now you see here the cable, this particular cable profile, that what you see here, it is making an angle d alpha, okay. And if I draw a vertical line right in the middle, this is going to be d alpha by 2, and this is also going to be d alpha by 2. Then that from trigonometry you can find that with respect to horizontal of this force is going to make angle of d alpha by 2, right. So now what we are trying to say here is, when I am applying a pre-stressing force P on the cable, at a distance, if I move away from the jacking end in the opposite direction, the force is going to be lost. Why? Because the friction force is going to be there, right, which is, let us say this dP is your friction force that is there in the small elemental length of the PT cable. Now at this right end, then the force that is going to be left is P minus dP, and so this is what we are saying. So you can see P, and the right end you have P minus dP, because there is a friction that is there on the surface which is dP, right. Now we have to find the relationship between dP and N, okay. So if you look at the free body diagram of the cable is in contact with the duct. The duct will push it down, right. There is a friction, always when there is a friction, you are going to have a normal force that is coming from the surface where it is rubbing against, right. So, let us look at now. If for this particular cable, if you look at only the vertical force equilibrium, and you can see that P into sin d alpha by 2, which is moving up. So, if I take moving up as positive, this as downward, then you can see that P into sin d alpha by 2, and the right side you have P minus dP into sin d alpha by 2, and the normal component of the force is, because you see the cable is actually pushing it up, that is the reason this N is acting downward, right. So, then N has to be minus. So, if you simplify that, dP is very small and sin d alpha by 2 is also too small. This two small products, when you multiply, it will become even smaller. So, that can be ignored. So, you can see that P sin d alpha by 2 plus P sin d alpha by 2 should be equal to N. Now, we know that this will become 2P sin d alpha by 2, and right. So, this will become when sin alpha is small, sin d alpha by 2 can be approximated as d alpha by 2. So, you will find that this is basically 2P into d alpha by 2, which is nothing but P into d alpha. So, that is what we have here, right. So, which is equal to N. Okay. So, we can say that by friction, now we can find, now that we have established a relationship between N and the d alpha. What is the angle d alpha? D alpha is the angle change that is happening for the cable profile of a small length, right. D alpha is the angle curvature, that what the curvature cable is that is subtending is nothing but your d alpha. Now, what is the dP from curvature? Now, I can find a relationship, right. So, what is dP? dP is nothing but, we know that, which is going to be mu into N. Now, that I know the relationship between N and P d alpha, we can write that the friction force that is lost to dP due to curvature is nothing but mu into P d alpha. Okay. Very simple derivation using the free body diagram of the cable. Now, when you take the free body diagram, you also look at all the forces that are acting on it, right. So, N is the force, normal force that is acting on that, and dP is your friction force, and these are the two forces that are acting on the cable. So, you can clearly see here that if I know the coefficient of friction, and this is the coefficient of friction of the two interfaces, and P is your pre-stressing force, and d alpha is nothing but angle or curvature angle by the cable. Okay. So, if I know between the two segments what is the curvature change, and if I know the initial pre-stressing force, and if I know the coefficient of friction between the two interfaces, then I can calculate my friction losses mu into N, which is nothing but mu into P d alpha, right. So, now wobble effect, what is the wobble effect? Now, as we have explained this clearly, the actual this black color profile is nothing but your intended tendon profile, but actually in field there will be local wobbling that will be happening. The cable will not exactly follow. So, you will have this local undulation that will happen like this. So, that is what we are saying due to wobbling. Now, wobble effect also that will create the frictional losses. That friction due to wobble is typically expressed as K into P dx, where K is nothing but your wobble coefficient or coefficient for wave effect, and P is your initial pre-stressing force, and dx is the length over which, the more the length over which you are calculating the loss, more will be the loss, right. So, more the waviness, more will be the friction loss due to wobble effect. So, the wobble effect due to loss can be written as K into P dx. Again, now, so what we typically do is the total drop in pre-stress over the length dx is written as mu into P d alpha. This is coming from curvature and this is coming from wobble. We add these two things and then say that is a friction loss in the cable. Okay. So, which is mu into T alpha plus K into P into dx. Now, this is a simple, you can form a simple differential equation, and then can be used for solving the express P in terms of x. Basically, what we are trying to see is, depending upon what section that x that you are considering, you should be able to calculate how much force is lost due to friction from the jacking end to the section where you are considering. So, we need to find an expression for this P in terms of x. Now, let us see how do we do that. So, this is a simple differential equation. If I bring the P down, then we can express this differential equations in this form. dP by P is equal to K into dx and mu into d alpha. Now, you see here alpha varies from 0 to alpha, where the total curvature change can be expressed in terms of radians, and x is basically the distance at which we are calculating, and alpha is also from at a distance of x, okay, how much the curvature angle has changed for a distance of x. Now, this when you solve it, you can ln of Pj by Px is equal to Kx plus mu alpha. Now, Pj can be expressed as Px into e to the power of Kx plus mu alpha, and I want to express Px in terms of Pj. So, if you reverse, then you find Px is nothing but Pj into e to the power of minus Kx plus mu alpha, and for small values of mu alpha plus s, and the above expression can be simplified by Taylor series expansion like this. So, you end up with this very simple expression, Px is nothing but Pj into 1 minus mu alpha plus 1 minus mu alpha minus Kx. So, if I know for any distance how much is the curvature change alpha has happened, and distance of x that I am considering, then I can directly calculate what will be the force that will be left after friction loss, which is nothing but your Px. Okay. So, this is the way that it is going to happen. Now, you see this is the initial jacking force, which is Pj, and it will keep on reducing because the alpha, the curvature change is going to be cumulative. So, right at this point, if I am calculating, this is Pj when I am doing it. So, from here to here, how much the curvature change has happened, that I have to use alpha. Similarly, if I am doing it here, from here to here, how much slope change has happened in the cable profile, that alpha I calculate and then put it in here. So, it is a cumulative effect. So, the net change in the curvature I have to put. So, that if you do, that is the reason you see here the pre-stressing forces keep reducing as you go from one end to another end. So, if you are not careful, then your friction losses can be quite significant, and especially in a post tension system, because I can do the post tensioning for multiple spans at a single stretch, right. So, 3 or 4 spans can be continuously stretched. So, when the cable is changing its profile, your cumulative change in the alpha can be quite significant. Then though you may apply at one end 75% of your ultimate strength, but other end you may end up with very less significant pre-stressing force that may lead to some performance issues from the design point of view. Right. Now, we know, so this is the Px is the pre-stress at the distance x from stretching after all the friction losses. This kind of simple expression can be used for calculating the loss. In fact, for post tension system, friction losses can be quite significant if you are not careful. Okay. So, how do we tackle that is by doing the pre-stressing in multiple stages, so that you get an average pre-stressing force along the entire length of the member. Now, how do we do that? So, you see here, I have, for example, you see here, this is a 3-span system, right. So, from here to here, if you look at it, the net cable change, the curvature change of the cable can be quite significant. So, typically what we do here is, let us say I have 10 tendons. Okay. What I do is 5 tendons I stretch it from this side, 5 tendons I stretch it from this side. So, let us say I am stretching it to 80%. So, this is the way 80%, and this is the 80%, because now I am stretching it from 5 cables from this side, 5 cables from this side, right. So, you will have force like this, and then it will come and then it will go like this. So, at the middle you will have the least stress, right. So, you have to be careful, right. So, now what we do is, okay, now once you release this, then immediately there will be a loss in pre-stress, okay, that we will talk about. This is basically from anchorage slip, that there will be a loss in pre-stress, and then due to reverse friction again it will go up and then it will go like this. So, you will see here there are zones where you have much lesser than 80% loss, okay. So, when the stress the stress is released from 80 to 60, this is the profile that you will have. But what we want is, we want an average stress along the entire length of the same, nearly same pre-stressing stress or force we want along all the 3 spans. So, what we do is, we stretch it to 80 and then when I release it to 60, it comes down, right. Then again what I do is, I stretch it back to 70. So, in this way what I will have is, I will get this kind of an average stress. So, this kind of multiple levels of pre-stressing can be done, which will help in getting an average pre-stressing stress along the entire length of the span. Let us look at an example problem. Here you have a 3-span continuous post-tension beam, and it has a symmetrical tendon profile, and it is made out of series of parabolic segments, and it is having 19 numbers of 12.7 mm strand, okay. So, that means 19 numbers are there, and ultimate strength is 1860 megapascal, and they are all simultaneously stressed, okay. So, you note this word, they are all simultaneously stressed. So, what is the meaning of that? There is not going to be any elastic shortening, okay. When you do only sequential stressing, you will have elastic shortening. In this case, you have simultaneously stressed, okay, from both ends, this also, right, and then they are anchored. Now, the tendon properties are, area of the tendon is 2407 millimeter square, modulus of elasticity is this, coefficient of friction is this, and K is point. This is a wobble coefficient, right. So, this is the wobble coefficient. Okay. And this is the geometry of the beam that is already given, right. So, what you have is, the first span is 16 meters, and with the point of inflection in the middle, and your the cable profile at a distance of C, for example, okay, say the first span is actually 8 plus 8 plus 2.5, so 16, 18.5, and then the next span is again, you know, it is a symmetrical thing. So, you see here the cable eccentricity is also noted here. Here it is 0.45 meter, here it is 0.17 meter, and here it is 0.35, and here it is 0.35. Okay. So, this is the symmetrical point. Okay. So, you can, and it is a 3-span system, exactly symmetrical on the other side as well. And the dot points are basically your inflection points that it is showing, where the slope is changing its curvature. So, the black points what you see here, these are your inflection points. Okay. Right. For this particular beam, that now what we are going to do is, we are going to look at what are the friction losses. Okay. Now, let us look at, now this is the geometry again of the beam, and with the cable profile like this, and each segment, now what we do is, we are going to convert them into segments from A to B, B to C, C to D, D to E, and E to F. Okay. Right. So, and X is moving towards right is considered positive, Y moving downward, it is considered as positive. Basically, our idea is to create the curvature change of the cable profile from each segment, A to B, B to C, C to D. How much the curvature is changing, that we have to calculate alpha, and the wobble coefficient, we know that that also we will be using it. Now, how to calculate the cable profile? Okay. So, you see here, when I draw a tangent here like this, when I draw a tangent at this point, the total angle change is nothing but it is going to be alpha 1 plus alpha 2. So, that is what we are trying to calculate between the two segments. Let us say I am calculating from this scenario at this point to this point, right. The total angle change of the cable profile is nothing but alpha 1 plus alpha 2. Now, I need to also know what is the slope of at each point, right. So, to calculate the slope of the cable profile at each point, I need to form an equation for this cable profile. So, let us look at now how do we form that. Similarly, from here to here, if you look at it, the total angle change is going to be 2 alpha 2, okay. So, from here to here, okay, this is alpha 2 and this is alpha 2. So, at this location is going to be 2 alpha 2, okay, that is what it is written here, right. Okay. Now, let us look at now. First, the pre-stress in the tendon at the stretching end is 0.7 into 1860 into 2000, okay. So, this is 0.7 FPU multiplied by AP, okay, will give you 3134 kilonewton. Now, the tendon profile is typically parabolic, and we know that the parabolic equation is y is equal to ax square plus bx plus c, and we know the boundary conditions. When x is equal to 0 here, y is 0, right, and at x is equal to 8 at this location, we know that y is equal to 0.45, and similarly x is equal to 16 at this point, y is equal to minus 0.1, y minus, again y downward is taken as positive, upward is above the CGC, it is considered as negative. So, we know the boundary conditions of the segment ABC. So, I can calculate the profile for this cable, right, and then we have like this, we can calculate the cable slopes at each points and then the change in the cable slope. So, after substituting the boundary condition for the tendon segment ABC, we are finding the equation for the profile as this: y is equal to minus 0.00836 x square plus 0.123 x. Now, what is the change in slope in radians is nothing but alpha is, for this is the cable profile, this is dy by dx is nothing but first is derivative of this equation will give me the slope, and the initial slope I am calculating at different points, and initial slope at A is taken as the reference. So, this point I am taking it as a reference, and then subsequent changes are all I am going to the slope at A is that is A is equal to 0, and then change in the slope at all the points are considered with respect to the point A. Here it is point A, right. So, this is the point A, that is your reference point, okay. Now, when you do that, this can be tabulated like this: at point A, x is equal to 0, at point B, x is equal to 8, at point C, x is equal to 16, at point D, x is equal to 18.5, and E it is 21, and F it is 28, right. And alpha we have already found the equation, right. So, here alpha we found, the slope at x is given as minus 0.0167 x plus 0.123, right. So, at each point if I substitute x, I get my change in slope, okay. This is basically change in slope, right. So, we are calculating with reference to A, right. So, if you substitute that at x is equal to 0, the change in slope is going to be this, and at B it is going to be 0.0106, at C it is 0.155, and so on, so on. Now, what is mu alpha plus kx? Here alpha is 0, the change in slope is 0, because though you may have a slope for the cable profile, the change in the cable slope is 0. So, it is going to be 0, and at B it is going to be 0.022, at C it is 0.063, and at D it is 0.091, so on, so on. And what you see here is this total value of mu alpha plus kx is always keep on increasing, because the net alpha is always going to change, because we are looking at the cumulative change in the slope, right. And e to the power of minus mu alpha plus kx, when you put it, it is going to be 1, and here at B it is going to be 0.979, and at F when you go, it is going to be 0.854. So, that means we know Px is nothing but Pj into e to the power of minus mu alpha plus kx. So, this is your initial force 3134 and it keeps on reducing, and as you go to the symmetrical location of the midspan of the second span, you get a force of only 2675, right. So, it has reduced from 3134 to 2675. You can find out the change in the pre-stressing force happening because of the loss in friction happening from curvature and wobble effect, right. So, you see, because now here this example we stretch it from both sides. So, that is the reason at the mid location of the second span the force has dropped from 3134 to 2675 kilonewton.